Hello, so today we are going to be looking at 2.1, Basics of Functions and Their Graphs. You can read the objectives for yourself. Don't forget you can always find the annotated notes in Blackboard. So here's a formal definition of a relation and a function. It also defines domain and range in more than one way, where domain is the input and range is the output, or the domain is the x values and range is the y values. So the big idea behind functions is to make sure that every x goes to exactly one y. So your x values cannot repeat. So if we try to define the domain here, we would take and list all of our x values. And we usually like to do this from least to greatest. So our x values here are 7, 20, 31, and 47. And so that's just our x values here. You see 7 occurs twice, but we only need to write it once. Knowing that the 7 occurs twice, we know that these y's don't match. They're not the same y's. So this is not a function, because this x goes to two different y values. We can't have that. So let's go ahead and finish this problem by listing the range. Again, you're just writing the values that are in the y position from least to greatest, and you don't need to write values that repeat. So this here, we're just determining whether it's a function or not. And remember, what comes down to being a function is if the x value or the input value only corresponds to one output or one y value. So this one here is not a function because the input of 9 gives us two outputs, -5 and +5. This one is a function because every x goes to exactly one y. And the same thing here. This one is a function because every x goes to exactly one y. We don't care if the y value is repeated. It's just the x value that we're concerned with when it comes to a function. So for each one of these, we can use the vertical line test to determine if this is a function. The vertical line test just says that if you move from left to right with a vertical line across your graph, if your graph touches the line twice at any time during the graph, then it's not a function. So we can see here that this one is a function, because it is a straight line. It doesn't curve back on itself in any way, so it's definitely a function, because when I move a line from left to right, you can see regardless of where I draw the line, it's still a function, right? I'm not hitting the graph twice. Same thing here. Parabolas are also functions. So lines are functions, quadratics are functions. We can see here that this is not a function because I hit this graph twice when I draw the line at this point. This is a function because it doesn't curve back on itself. It has a curve to it, but it doesn't curve back on itself. This is a function because, again, I'm moving from left to right. But here, this last one is not a function. And again, it's because I can mark two distinct points on a vertical line. So this talks about the function notation, so input versus output, which we just talked about a little bit. I'll let you read the next few slides on your own, just pausing slightly for you to have time to pause the video to read on your own. So on this slide here, we want to substitute the given value in for every x in the expression and simplify completely. So this is when we're solving a problem given a particular value. So this time we want to find the value of f of x when x is -2. So if we substitute in -2 into the formula, we get -2 cubed minus -2. So -2 cubed would simply be -2 times -2 times -2. Well, negative 2 times negative 2 is positive 4 times negative 2 gives me a negative 8. Here we have a minus and a minus next to each other, so that actually can be written as plus a positive. So we have negative 8 plus 2, which gives me a negative 6. So my input was negative 2, and my output was negative 6, or if you wrote it as an xy point, it's negative 2, negative 6 as the point. So let's take a look at a few more. Here we're given g of x equals x squared plus 3x plus 5, and we want to find each of the following. So now we're putting a whole term in. So we have g of x plus 3. I guess I can just substitute it in. I don't need to rewrite it, huh? So I get x plus 3 squared plus 3 times x plus 3 plus 5. When we do this type, we need to go ahead and simplify. So when I see x plus 3 squared, that means I'm doing x plus 3 times x plus 3. You cannot just distribute that 2 over those two different terms. You actually have to multiply them out. So I'm going to go ahead and distribute on this next term to save me some writing and some steps in the future. And so here I'm actually going to do this multiplication of x plus 3 times x plus 3. So that's x squared plus 6x plus 9. And then I'm just bringing down the other terms that we already did. And then I'm simplifying by combining like terms. So we have x squared plus 9x plus 23. So let's take a look at this next one. So we have negative x squared plus 3 times negative x plus 5. When we look at this problem here, a negative times a negative is a positive, so we just get x squared for this first term. Then the next term, 3 times negative x, will give us a negative 3x and plus 5. And that's in simplest form. So this one might look more complicated because it's a rational function, but it's not. You're still doing the same process here. So let's take a look at a couple of the problems. So if we substitute in 3 for x in this first one, we would do our exponents first. So this would be 3 squared would be 9. And so when we continue this problem, 4 times 9 would give us 36. And then 36 minus 3 would give us 33. And then we could reduce to give us 11 over 3 as our final answer. So here we're substituting in negative 3. And what I want you to remember is that a negative squared is just a positive. So you're going to get the same thing that you got in the previous problem. So let's go ahead and do it. Negative 3 times negative 3 would give us a 9. And negative 3 times negative 3 would give us a 9. So you see these two are the same step here, which means that our final answer will also be 11/3. So this last one, if we substitute in a negative x for our x, you'll see again, because the exponent is even, we're going to get the exact same problem we started with. So another thing we need to be able to do is find a function on a graph. So in this function, when it says f negative 1, what it's telling you is that we want the y value for when the x value is negative 1. So we can locate that. This is negative 1 for x, so our y value there my screen is off a little. Give me just a second. So the y value there is positive 3. If we look at where f is 0, so we go to the x-axis and look at where it's 0, we're looking here at 5. And where f is 1, we're looking here as well, and we see it's also at 5. So here we're being asked for f of x equal to negative 4. So this time we're given our y value and we want to find our x value. So when f of x equals negative 4, we go down to negative 4 on the y-axis and we see where our x is, and our x there is at negative 1. So in this case, x is negative 1. For f of x equals 0, same thing, we're going to go to where y is 0 and look at the x values that occur. And we actually have two here. We have x can equal negative 3 and x equals 1. So this is the case where f of x is equal to y and you're finding x. So the next several slides is just reading formal definition. So as I said, I'm going to pause just enough for you to pause the video and read through the slide, and then unpause when you're ready to look at the next slide. So when we get to this slide here, we can go ahead and talk about this slide. What I want to point out is that there's two ways that you could be asked to write domain and range, or really any kind of interval. There is what's called set notation, and there is interval notation. So this would be set builder notation, and this would be interval notation. So you need to pay attention for how your answer is being asked for. So let's take a look at these. We want to find the domain and range of each graph below. So remember, domain is your x values. So we're looking from left to right. So if I look at where x goes from left to right on this graph, we're going to start at negative 3 and we're going to end at positive 3. And I'm using the brackets because these circles here are closed circles, so those values are included. For our range in this case, we're going from bottom to top. So we're looking here at negative 3. We do have closed points at negative 3, so we're going from negative 3 to our graph has a maximum at positive 4, and that point is included because that's a solid line there. So we are going to use a bracket. If we take a look at this next one for domain, again, we're looking at the x's. So this is a closed circle at negative 5. So we have bracket negative 5, but we have an open circle at positive 5. So we're going to use a parentheses for that open circle because we go up to 5, but we don't actually touch it. And then for our range, we're looking from top to bottom, from bottom to top. So our bottom point is right here at negative 10, and that is in the closed circle, so bracket. And then our graph tops out at this open circle here at negative 4. So that value is parentheses again because that circle is open. So some graphs you can determine the domain and range really easily by just looking at them. This domain here, it starts at negative 4 when we're going from left to right, and it is actually touching that point. And then the arrow goes on in the positive direction forever. So we're actually going to positive infinity here. And when we do a infinity sign, we always have a parenthesis because you cannot contain infinity. So when we're looking at the range here, we see that when we're going top to bottom to top, we're starting here at 0, right? We're starting here at 0. And because this is going to continue in an up trajectory the whole time, it is also from our value where we start of 0 to positive infinity. On this second one here, we see that our arrows they're going left and right forever, both of them. And so we're going to go from negative infinity to positive infinity for our domain. Our range, our graph doesn't start until 1, right? And that is a closed point. But we are going to go up forever. So that is infinity. So let's do a couple more. Here, if we take a look at these graphs here, our domain in this case is from negative infinity to positive infinity. Again, because we're going right here forever and left here forever. But our range is also negative infinity to positive infinity because we're going up forever and going down forever. If we look at domain and range for this parabola, the domain for all parabolas is negative infinity to positive infinity, as long as it has these arrows on the end, meaning it goes on forever, right? So, because it is traveling in both directions forever. Whereas range is always either a minimum or maximum point we have to take into consideration. So our minimum point is here at -4, which is inclusive. And then we're going to go up forever because of those arrows at the top there. So we're going to positive infinity. So the next main idea I want to cover with you is intercepts. So x-intercepts and y-intercepts. X-intercepts are just where we touch the x-axis. So if we look at our x-intercepts here, we have one at -3, at -1, and at 2. So our x-intercepts are the points -3, 0, -1, 0, and 2, 0. And then y-intercepts are just where we cross the y-axis or touch the y-axis. So that is occurring at -6 here. So that's the point 0, -6. So on this next problem, we want to just kind of tie all of the ideas together. And let's go ahead and put an arrow here. I just want you to realize that I do think there is an arrow right there at the end of that graph. So let's first determine the domain here. So our domain, again, is going from left to right. So we see we're going to go left forever here. But we stop abruptly right here with a closed circle. So we're going to go from negative infinity until we get to 5. And it is a closed circle, so it's inclusive. For range, you see we're going down forever. So we're going from negative infinity. And then we have a maximum here at 3. So from there, all right, sorry, I needed to pause the video to get rid of some of the background noise. So we'll continue here. So we have our x-intercepts. So again, that's where we touch or cross the x-axis. So we have one at -1 and again at that point at 5. So our x-intercepts are -1, 0, and 5, 0. Our y-intercepts are where we touch or cross the y-axis. And so if we kind of zoom in here, we can tell that we're touching the y-axis right there, kind of halfway between 1 and 2. So our y-intercept in this case is 0, negative 1 point, or positive 1.5. All right, so then we can take a look at F2. So remember, when we're looking at F of 2, we're looking at where X is 2 and finding the Y output. The Y output here is 3. And then we want to know any values where F of X is negative 5. So in that case, we are going down to negative 5 on the y-axis and seeing what our x would be in that case. So our x in that case is negative 3. So x is equal to negative 3. So the last topic we're going to cover today is piecewise functions. So for piecewise functions, we have functions that apply for different intervals. So we see when x is less than negative 7, we're going to be applying the function negative 4x minus 20. When x is between negative 7 inclusive and 1, the function is just going to be equal to 1. And when x is greater than or equal to 1, the function is going to be x plus 9. So when we're doing these and we're given a value for x, the first thing we need to do is see which interval it falls into so that we know which function to use, which part of the function to use. So for negative 9, we can see that for part A, h of negative 9, we have negative 9. Well, that's less than negative 7. So we're going to be using this first function here. So we have negative 4 times negative 9 minus 20. So when we do that, negative 4 times negative 9 is 36 minus 20 gives me 16 as my answer there. So then on this next one, we have h is 1. So when we're looking at the value of 1, that's going to work here where 1 is greater than or equal to 1 because of the inclusivity of the 1 here. So we're going to be looking at this function here in this case. So we're going to have 1 plus 9. So we get 10 as our solution there for part B. So for part C, we have negative 4. Well, negative 4 falls between negative 7 and 1, right? So for this one, we are just going to have 1. So h of negative 4 is equal to 1. And then for the last one, 3 is greater than or equal to 1. So we're also going to use this third piece here for h of 3. So we substitute in 3 plus 9 to give us 12. And so that is the conclusion of 2.1.